Well, this page is directly out of your book, and we're going to add to our thinking today just the fact that our engineering is basically connected in some way. And I want to highlight kind of the major ones. A fixed support, this number 10 one. The fixed support means it's like bolted to the wall. And I think our first example today is going to be dealing with that. But notice that actually, because it's bolted to the wall, it actually provides, that wall connection actually provides all three of these forces. In other words, it isn't letting it move in the Y direction. So it's got a force in Y. So it's not, because it's attached fixed, it's not letting it move up and down. It's not letting it move, in or out from the wall, and it's attached, but it's also providing a moment in the sense that it can't rotate either. So we need to add, basically, if we determine that a connection to the wall is fixed, then we've got to basically add all three of those forces to it. So our free body diagram has always got to show all of the forces that are acting on something, and we've got to, through equilibrium, set those equal to 0. And so fixed is an important one. It's pretty common, and it's got 3 different forces, and I got to think about all those. Whereas look at this second one. This is another classic one. It's pin connected or hinge connected. And again, there's a pretty decent drawing of it there. You can see the pin right here kind of passing through that member. Howdy, Thomas. And so because it's pin connected, it again is not going to be able to move up or down. So there will be a force in Y. So it's not going to let it move that direction. It's also not going to let it move in the X direction, but it actually could pivot left and right. So notice there is no other force kind of hooked to that. There's not a moment force, because that can't stop, since it's not fixed connection. It can't stop it from kind of rotating for that angle right there. That angle can change, it can rotate. So it won't move. It's not going to move in the X or Y direction, but it will rotate. So pin or a hinge. So you got to pay attention to drawings when you see that. Or there's even one, and this is kind of common for these are the 3 classic ones. A rocker. This is the way most bridges are actually supported. So the problem is things are going to move a little bit. So notice this isn't attached at all. It's literally just sitting on something. It's just sitting there. So what is that able to do? Well, notice in the figure over here, it's only able to produce a force that is perpendicular. That's what this line represents. Perpendicular to its attachment. In other words, I can't say it can support it up, down, right, and left. It's just sitting there. So the only force it can basically produce is that force pushing directly off of it. Let me give you just kind of an interesting example that let's see, do I have this pulled up? Let me try to share this with you. So I'm just going to show you something quickly that I'm kind of constantly doing. So, and interrupt if you can't see things clearly, but I think you can here. So this is a truss design for a house. And for the most part, when I'm designing a house, I don't really care where they put the trusses, unless, except for these red ones. These red ones are called out because they're double trusses and they're actually carrying more weight. Maybe the rest of the truss design, I won't explain it, but the rest of the truss design actually hangs or rests on this truss. So it has more weight on it than usual. So I don't know if you can picture this. It's not super important that you can, but notice this is called truss H1A, and this is the outside edge of the house. So it's kind of angling uphill until here, and then it turns and goes downhill, and then it's actually flat across there. this is actually what that truss looks like. So notice up here, it's a 2-ply truss. And so the thing I'm looking for as a designer to make sure that this can be supported is to say, okay, well, this is a very special truss. It's got a lot more weight on it than usual. And the thing I have to look at is, well, how much weight does it have on it? So I just want you to look at this with me because it's interesting. So notice there's, let's see. I think you guys can see this okay, but notice it's actually sitting on 3 different walls. There's a wall over here. Notice that's labeled B, and then there's a wall in the middle that it's resting on too. And notice some of its webbing is actually designed to push right down on top of that wall, and that's at location L. And then there's another section over there at the end called J. And so it's sitting on those 3 locations. And so what I got to do, J, B, and L, is I got to look down here at these reactions. And that's kind of a key word in engineering is the concept of a reaction. So notice I'm looking at gravity. And these are, well, kind of like that rocker support a minute ago. They're just sitting on top of this. So the only force that these walls are producing is just basically J right over here at the right. We're told that that's got 1,146 pounds of force on it, which isn't too much. Dirt holds 1,500 pounds per square foot. So that's less than 1 square foot. So generally I don't have to do anything special with the existing foundation in that situation. B over here has even less weight. It only has 978 pounds. But then L here in the center, that's got 2,745 pounds on it. And so that's the reactions based on all the different roof loads that are all across this truss. That's how much force is kind of sitting at that location. So what I've got to do then is figure out where this truss is. Let's see, do I have any dimensions to it? Doesn't look like you give me any great dimensions to it. I think it's 6 feet from this front wall right here. But basically I got to decide where is that. So you may remember that the 2,700 pound weight was at L in the middle here, the big one. That was the 2,745 weight. So basically I got to go to this location inside the house, and I've got to put a larger concrete footing there to support that, because the gist of it is that's more than 2 1,500. So that's like, I need a 2 square foot footing right there, because again, I'm just sitting this house on the dirt, and dirt can't push back more than 1,500 pounds a square foot. So if I only have a small foundation underneath this, that's not going to work. Let me see, is this the same one? Let me show it to you. So notice in this case, right where that landed, in my case, it actually happened to land right on the top of a door. So the weight is centered over the top of a door. So that's going to transfer the weight over to this side and over to that side. And so I basically just had to put a note there that those 2 studs holding up that beam that goes over the top of the door need to be there in order to support truss H1A. Anyway, maybe we'll get a chance to play with that a little bit more, but this concept of a reaction, again, my goal is to, well, equilibrium. I want however much weight is on this house, I want it not to move. So I've got to make sure the foundation's big enough to do that job. Most foundations on houses, just out of curiosity, are only 12 inches wide for a 1-story house. So basically this pink line that you're seeing right here going around the outside of the house, that's 12 inches wide. And that holds all normal locations. But anytime there's a beam, in this case right here in the garage, you may be able to picture that, if you have a garage, there's a giant hole in the wall. And so in that case, I had to have a beam over the top of it to support the roof. But that took a lot of weight on top of that beam, and it put quite a bit of weight over here at the side. So I had to beef that footing up. it wasn't large enough. It's only 12 inches wide. I had to beef that footing up to 24 by 24 to be large enough to kind of carry that load. And there's a few beams in the back, and so I have kind of big footings underneath the house too. Notice this one's really big, 34 by 34 by 10 inches. It's a really big footing. It's carrying lots of the roof weight, basically. Okay, well, anyway, that's just an interesting interlude. Let's sorry about all the coughing. So I gotta wait for a second to share other screen. Good, that didn't take that long. So armed with that, we're about to look at our first question, which also has a fixed support. So let's just take a quick second look at that. And maybe because I emailed it to you, you have a look at it. But let's look at 5:10, chapter 5. So notice this figure. Now they tell us in the problem, but can you tell that's fixed, supported to the wall? I can't really see any bolts and so forth. And so they did also tell me just to make sure. But notice this, nothing else is attached. I mean, that whole beam or crane arm or whatever the heck that is that's doing a job is just supported to the wall. So it's bolted or welded. Who knows? We don't really know. It could be a steel wall, and that could be a steel bracket. It could be welded. Or maybe it's a few bolts because the person wants to be able to take it on, take it off. But that's part of what this calculation's for. You can't just assume, oh, it's attached to the wall, everything will be fine. You actually got to know how much force is going to be pulled on the wall as a result of this. And then you got to make sure you have enough bolts or enough welds, or the wall is, sturdy enough not to kind of rip off. You can see here that there's 6 kilonewtons pushing down right here. And then we also have 4 kilonewtons pulling down over here. So you can probably appreciate this whole thing wants to kind of rotate down like that. It wants to rip out of the wall. So you can probably appreciate with that much force on it, this is kind of what it would want to do. It would want to rip away from the wall. In other words, if there was a kind of a bolt on the top of this that was bolted back into the wall, that bolt would want to kind of get pulled out of the wall as a result of this. And so it's actually very interesting to notice that because both of those forces are pulling down, this thing wants to rotate down, or what we would call negatively. And so I actually don't need as many bolts on the bottom of this, because the bottom is just going to kind of stick to the wall all by itself anyway. So I don't really need that much down there, but I might need a whole bunch of extras on the top. So notice it's interesting. It's like you don't just kind of put bolts over there. You got to think about where are they and how much force. And really that's what this calculation is all about. So it says determine the components of the support reactions. There's that word reactions and support against the wall at the fixed support. So they're telling us, in case we can't see it from the picture, this is a fixed support. So the good thing is there's really nothing new to this. I could draw a free body diagram for this, like redraw it, but out of laziness, I think I'm just going to use what's over here for now. Maybe I'll change my mind in a little bit. But remember, because this is a fixed support, we've got a force in Y that we can count on from the wall. We've got a force in X that we can count on from the wall. And let's see. And notice I don't necessarily know which way to draw those. I drew them sort of in the positive directions. If I'm wrong, then I'll get negative answers to those, and that's okay. But notice from your force connections sheet, you kind of have a natural way of doing it. Notice what they're doing is drawing them all positively. Up is usually positive y, right is usually positive x, and then is it this direction? Isn't that a positive moment? So you can actually assume anything you want and just let the chips fall where they may. So that's around point A. So does it make sense? I have a complete free body diagram now. I had two forces that were already on this that were given to me going in different directions. And now I just added my own other three forces. And now I've got to basically do this, hopefully simple calculations that pertain to equilibrium. This is a two-dimensional drawing, so I don't have to worry about Z direction. But as long as the sum of the forces in X and the sum of the forces in Y, since that's the only two directions I've got to worry about here, and the sum of the moments around A, if all of those are zero, then good, this thing's not moving. So I'm going to be able to solve for those forces of X, Y, and moment of A. And then I can sort of make sure that that wall and bolts that I've chosen and so forth are sufficient to do that. So all we're really adding in this section is just what's going on at the support. I got to recognize what kind of support it is and what it can do, what it can resist, add forces for it, and then include those in all my calculations. I don't really know which one to do first. Is it easier to do some of the forces in X first, or some of the forces in Y, or maybe some of the moments around A? I actually don't really know. I think I'll just launch in order. If we're sort of wrong, then we'll figure it out. So let's see what's going on in X. What do we have going in X? Well, notice that 6 kilonewtons is going straight down, so it has no effect on X. That 4 kilonewtons is definitely pulling to the right. But you should notice that at 30 degrees, it's not pulling directly right. So to get the component of it that's going right, I'd have to do cosine. So I've got to do a modification of the cosine of 30, and that will tell me. And notice I'm paying attention to the units. They're both kilonewtons here. And so basically all my forces will be in kilonewtons. So I'm just remembering that. So that's it. That's the only thing pulling to the right. Does it make sense then that my force of X, if you will, is sort of drawn in the wrong direction? That this whole beam is being pulled to the right. So I could come back and change that and say, well, clearly force of X is actually going to the left. Or I could just kind of continue and let the chips fall where they may. I see it's aiming to the right, so force of X, that equals 0. So if I solve for the force of X by subtracting 4 cosine of 30 over to the other side, let's see. I'm in degree mode. 4 cosine of 30 is 3.46. And it does not come out positive. It just means that my arrow's backwards. Again, you're free to just leave the picture alone and say, well, there's the arrow, it's aiming to the right. What's the actual answer? Negative. Or you're free to go back and say, even after the fact, if you didn't notice that ahead of time, you can say, no, I'll just turn that thing around. Actually, it's going that direction. That's okay too. Either one is fine. So 4 kilonewtons is pulling to the right. The wall is going to be able to pull back from the left. And of course, you can appreciate if you don't put enough bolts, maybe that's not going to happen, right? And there's two things that could happen. One is it could rip the bolt in half. The other is it could yard the bolt out of the wall. Like if the wall was just made out of sheetrock or something and you put a bolt in it, maybe that 4 kilonewton force, remember that is 4,000 newtons of force. That's a lot of force. Maybe that rips the bolt out. The bolt doesn't get hurt, but it just isn't threaded well enough to be able to attach, or maybe it's welded and the welds aren't good enough or whatever. But again, what this tells us is we better make sure that's attached to the wall in such fashion that it can hold 3.46 kilonewtons or more for safe reasons. Otherwise, this is not going to stay in equilibrium. So this is not just automatic. Like now you have to go design the connections at the wall to do that job. So apparently that wasn't a bad choice to choose that first. That worked out okay. Can you tell that I got the force of Y kind of right by logic? Because isn't the 6 and the 4 both going down? So wouldn't the wall basically have to pull up in order to stop that? So, you know, that's good. At least the force of Y is going to come out the correct sign here. I can see that now. So what's happening with the force in Y? Well, I've got -6 kilonewtons going down. Don't have to modify that. I've also got 4 kilonewtons going down. But to get the Y coordinate of that, as I hope you know, that would be this direction. That's opposite of 30, that's sine. So I've got to multiply it by the sine of 30. And then I've got the force of Y going up. And that all has to be equal to 0 according to equilibrium. So if I add 6 and 4 sine of 30 to the other side, I end up with exactly 8, which is kind of cool. So I got a positive. As I said, I mean, the orientation is going in the right direction. The drawing was correct as it is. Again, can you picture what happens over there at the wall? If you have, and I guess I would like to, I'll probably erase this, but I would like to kind of explain it a little bit. If this is your kind of your attachment, and you had a bolt going into the wall right there, maybe another bolt going into the wall down here, given that what's happening at A is this is going to be pushing up with 8,000 newtons of force, 8 kilonewtons. Does it make sense those bolts could shear off? We'll talk about this more later in this discussion, but notice the bolt's not being pulled on lengthways. It's actually trying to be kind of sliced in half like a set of scissors. So the part's stuck in the wall, but this thing's going to push up in the air. I could just shear those bolts right off, slice them off along, kind of perpendicular to their length, if you will. That's what a shear force is. So again, I got to have enough bolts. That's not going to happen. How many bolts does it take to avoid 8,000 pounds of shear force on this? You know, it could be 2 really big bolts, could be 4 smaller bolts, but that's something I would need to look up. So anyway, that's interesting. So far I'm able to calc everything in order. Like it wasn't like I got an equation that it had 2 unknowns or something. So this isn't that terrible. And lastly, what are the sum of the moments around A? Well, as you know, the moment is a force times a distance. So I got 6 kilonewtons pushing straight down, and perpendicular to that is 1.5 meters. So I'm very happy that that's perpendicular, so I don't have to do that much work. So 6 kilonewtons times 1.5 meters. So my units for this would be kilonewton meters. That's okay. If I wanted to switch it to newton meters and call that 6,000 newtons, and then go 6,000 newtons times 1.5 meters, that's fine. But I don't think there's any reason I can't leave this alone. And then let's think about what's happening at A here. We figured this out earlier, but just to write it down, we had a force in the X direction there that was 4 times the cosine of 30. I never wrote down what this was before, but it was 3.46. So that's actually what its X direction is. 4 times the sine of 30 is actually 2. So if I break this into its components, I basically have 3.46 going this direction. Notice I'm taking off from exactly the same location. So I basically replaced 4 kilonewtons, which, would you agree, is at a really weird distance? This is again a discussion we've had before. That's at a very strange distance from A. So I don't want to use 4 kilonewtons. I want to break it into its component directions, its X and Y, because from that, I'm probably going to be able to figure out what the distances actually are a little bit more easily. So I've got 2 kilonewtons and 3.46 kilonewtons. And now let's figure out what the distance, what those distances are from A. And notice it's not given, but I am kind of given this 1.5 hypotenuse right here. I'm given that right triangle. So in that way, I should be able to get this distance and this distance. So 1.5 times the sine of 30 is 0.75. So that's how long that distance is, 0.75 meters. 1.5 cosine of 30 is 1.22299, I guess. So armed with those distances, can you see how far each one is away now? So this 2 kilonewton force right here, kind of in the Y direction, notice it's basically this far plus that far. What is that? 3 plus 1.299, 4.299. And that's also, fix this for the previous problem, but there's 2 kilonewtons times, we said 4.299. So the one thing I got to be careful about that I thought about earlier, but I just wasn't thinking until now, is notice that's causing rotation in this direction. That's what we typically call negative. So the 6 kilonewton force is causing clockwise rotation, so that'd be negative. The Y component, that 2 kilonewton force, is also causing clockwise rotation, so that would also be negative. And then there's that 3.46 kilonewtons. And notice it's a distance from A of, well, that 0.75 that we saw earlier. 0.75 meters. Is that causing clockwise or counterclockwise rotation? Remember, I can move the force. So if I kind of move that force over to here, moving that 3.46 kilonewton force over to here, it's basically causing counterclockwise rotation as well. So all 3 of these are trying to get that to rotate counterclockwise. So that's also negative. Obviously, if I screw, go ahead, Connor.
Why is that 3.46 not 4.29 meters? Just like, because it's at the same point as the 2 kilonewtons.
Why isn't it? Well, the hypotenuse is 4, so that means the other 2 forces would have to be less than 4, since 4 is the maximum. If I do the Pythagorean theorem on 2 and 3.46 and 4, that does work, which kind of proves that I didn't screw up breaking 4 up into its components. Did I answer your question? I'm not sure.
No, because you did 2 kilonewtons in the, like, basically the force in the Y direction, and you multiplied it by 1.5, 1.5, and then 1.299, because it's coming from that point.
That's right.
So when you are doing the distance for the f of x direction, the 3.6 whatever, why is it not the same distance? Why is it 0.75?
Well, do you agree that this 2 kilonewton force right here, based on its location, is this distance away, 1.299, plus 1.5 for that distance, plus another 1.5. So that's a total of 3, then 4, and 1 more is 4.
I get it now.
So
We had to do the y distance away.
yeah, so just like the cross product, notice that's basically, this is a force in y. And we ended up multiplying it by the distance in x,
Okay.
because that's perpendicular to that.
Okay. My bad. I got it now.
Okay. And so I think this 3.46 is, in a sense, even harder to see unless you visualize it as I pointed out, kind of moving over to this location, because that's really where it is. And so it's this far away from A. And so that's where that 0.75 calculation comes in. That's how far it was away. So basically all 3 of those components want this thing to rotate counterclockwise. And so if it wasn't, I mean, you can probably appreciate if that was not a fixed support, if it did not have the ability to resist that, then this thing falls over. Like, that better be fixed supported, because that thing's rotating if it's not. Notice I drew this in coincidentally in the positive direction, counterclockwise. So down here, I would be kind of adding that to it and saying plus the moment around A provided by that fixed support. And so I got to solve that. So again, all 3 of these equations had just one unknown in them. So I could have solved any of them anytime I wanted to. So if I add all of those negatives to the other side, 6 times 1.5 is 9, plus 2 times 4.229. 4.299. I'm going to rewrite this a little more accurately. I had that as 1.299. So 2 times 4.299. And then finally, if I add 3.4 times 0.75 to the other side, well, that's pretty darn close to 20. So I didn't need to switch it into meters. I just needed to leave it as kilonewton meters. That's fine. Again, if I look in the back of the book, the answer could be in newton meters. That's fine. So notice that's a lot of force. That's a pretty big desire to rotate. So that's got to be attached to the wall in such a way that it can resist 20, kind of a couple moment, resist 20 kilonewton meters of desire to rotate. And as I said, that's mostly due to the bolts on the top. So this thing can be in equilibrium as long as you understand that the attachment at the wall is capable of these capable of those requirements, I guess I could say. So do you see why engineers call that reaction? In other words, that's the reaction at the attachment point of those 2 force arrows over there. That's the resulting reaction back at the wall. And so since it's fixed supported and I actually figured out how much force is on each one of those, then I just have to attach it in such a way I can do that. Awesome. Uh-oh. Every so often this thing panics. I'll come back in just a second. Thanks, Connor. No, I'm good. I've been coughing like this for a few days now, so
You coming down and getting a little bit better with it, or is it still feeling the exact same?
feels about the same. I tested negative, so I don't have COVID at least, but
That's weird.
it's painful to listen to somebody coughing, so that's why I thought I should just teach away.
The common flu's been eradicated, so it's pretty weird that you don't have COVID. I think it was like 1,000 cases or something last year of flu.
Yeah, I'm surprised anybody had it. So I want you to stare without reading this question. This is 512. I sent this to you guys as well. Notice it's pretty simple. It only has one force on it. But notice it's it looks like an I-beam, but notice its attachments. How is it connected? Do you see the hinge nature over here? Do you see that that's a pin support? So would you agree that if I came over here and put, I don't know, 10 kilonewtons of force on this, that this beam is going to rotate up in the air? Does that make sense? There's nothing keeping that from happening. So apparently this person's design, apparently that's never going to happen. Because notice it's not pin connected over there at B. So it's allowed to rotate, but it is pin connected. So as we talked about before, since that's a pin connection, I can assume that, and notice I have kind of two locations this time. So I can't just call this force of Y because I'm also going to have one of those over on the other side too. So I think I'm going to call this something a little different. I'm going to call it the force A in the Y direction. And again, at this point, I'm just assuming. I'll call this force at A in the X direction. That's the two forces that connection can provide, but it can't provide any moment. It's not a fixed connection. So what about that other connection? What's that connection called? That B connection over there? A rocker connection. And notice what's kind of cool about a rocker is that it can make adjustments, and that's why it's often used on bridges. It isn't stuck kind of in that position. It can actually rock a little bit. And so notice we're told it can only be perpendicular to the location. So in other words, this thing is pushing against the metal plate right there. So the only force you're going to get out of this what do you guys see right now? Every so often this thing just kind of blacks out for like 3 seconds. Did it go away and you just saw black and now it just came back again?
Yeah. And there's a little black square right now. Kind of like there's a window on top of a window or something, and we can't see the, yeah, you just moved it.
But you can see the whole drawing now.
So now, yeah, now that black window is gone and we're seeing just the drawing.
Okay. I guess I'm seeing what you see then. I don't know. I'm sitting here working and all of a sudden everything just goes black for 5 seconds every so often. I have a double screen. And I don't know if that causes it, but so anyway, do you notice that force of B that I wrote over there, notice it's not in X or in Y, it's in a totally weird direction. But thanks to that 30 degrees, does it make sense I could convert it to its XY components if I wanted to? And I probably will want to. Let's get this out of here since that wasn't real. I don't know if you can see this time, but because it sort of has reactions in two different places, it's a little hard to tell where the 4 kilonewtons is going to go, like how much of that 4 is going to go over to A and how much is going to go over there to B. You might guess, and you'd be right if you did, that because that 4 kilonewtons is closer to B over here, it's closer, then that means this support is actually going to carry more of that. If this had been perfectly in the middle, then half of the 4 would have been over here and half of the 4 would have been over here, but it's actually closer to this side. So what's interesting is like, okay, great. Well, what's the breakdown here? And I don't know if you can see this, but can you appreciate if I was to write right now a sum of the forces in, say, the Y direction? This time I'm going to have 2 unknowns because this is not cantilevered. It's got 2 different attachment points. In other words, both force of A in the Y direction and force of B are both pushing up. So they're both going to be working together to stop this 4. And as I said, maybe this one's gets a little more than half. Maybe this is like 2.5 and that's only 1.5 or something. But the problem is if I did a sum of the forces in Y right now, I would have 2 unknowns in that equation. I'd have a force of AY and a force of B. And so that's not so good. That could just mean, fine, I'll have 2 unknowns and then I'll need 2 equations, 2 unknowns, and I can solve it with a matrix. Or it could be that maybe there's one of them that's easier than the other. So remember, I've got a sum of the forces in X, some of the forces in Y, and some of the moments, and I've got to set them all equal to 0. So I'll show you kind of one of the tricks to this. Generally speaking, when you have 2 supports like this, it's way easier to do the sum of the moments first. I'll show you why. And the other problem is in this case, do I do the moment around B or do I do it around A? That's kind of the problem. Again, can you agree that I sort of have drawn my free body diagram over here? I sort of just stole the one that was already here. I replaced the connection with force of AX and force of AY. So, you know, if I was to draw it from scratch, it'd be so close to the same because all I would show is just the beam free bodied floating in midair. And what's going to keep it there? Well, all of those 4 forces. I've got to balance all of those 4 forces. So if I was to redraw it, that's what I would show. I'm not showing the dirt anymore. I'm not showing the connections. I'm showing the arrows that the connections are capable of providing. So again, out of laziness, I'm just skipping it. So let's see. Well, I haven't figured out what's going on at B. Let's just do some of the moments around B. So let's see, I'm thinking of everything is rotating around B right now. So I've got that 4 kilonewton force trying to get it to rotate this way. We call that positive because that's counterclockwise. So it's 4 times the distance of 2. Notice that's exactly perpendicular to 2. That's nice. So I don't have to make any adjustments. 4 kilonewtons times 2 meters. So there's a desire to rotate. Do you agree that force of AX is pointing directly at B? Therefore, the force of AX, although it has a force of some kind, has no distance. Do you agree with that? Last time, because of that angle in it, it did actually have a distance. But this is aiming right at B, so force of AX is not going to cause any rotation. Now, force of AY is going to cause rotation in the other direction, clockwise, that we call negative. So force of AY, which I don't know what it is, and its distance from B is 6 meters and 2 meters or 8 meters, and that's it. And notice force of B is also a distance of 0 from B. Therefore, the force of B is making no difference. And so that's all there is. And so that's why that was a good choice, because notice it only has one unknown in it. So I can actually solve this right now. And I can see, just doing this in my head, the force of AY is actually 1 kilonewton. And you may notice that I got it right. It's positive. So my my upward arrow happened to be correct because I got a positive answer. So that means my arrow was drawn in the right orientation. So I'm looking for all three of the reactions: force of AX, force of AY, and force of B. I'm looking for all three of those, and I found one. Let's see now, what should I do? I could redo another moment calculation. I could do it around B. That would be fine. It feels like at some point I might want to convert that force of B into its X and Y components. Let's see, what would those be? So this would be force at B in the Y direction. This would be force at B in the X direction. And notice I'm aiming that the correct way. I'm aiming that matching the force of B that I have. So let's see, I don't know about you, but that's kind of a confusing drawing. Do I use sine of 30, cosine of 30? Are you a little confused by that? Would you agree that what we're being told here is that this angle right there is 30 degrees? Which means, let's see, I'm just thinking out loud here, but that means that angle up there would also be 30 degrees. So what angle is that force of B at? It's perpendicular. I don't know about you, but I'm finding this kind of hard to think about. So this is force of B coming in right there, perpendicular to that. So that's kind of the hypotenuse, if you will. So let's see. I guess I could think of it as like, this is the force in X. Smaller pen. And that would be the force in Y. Remember, the actual force itself, the actual force of B is the hypotenuse, so it's going to be the biggest of the three. Well, let's see. So since this angle is 30 degrees and this angle is 90, that means this angle right here would be 60, which means this angle is 30. So So I guess I could say that the force of B in the Y direction is the force of B, but times the cosine of 30, since force of B in the Y direction is adjacent to 30. Notice it's like I had to get kind of creative with geometry to make sense of that. It wasn't obvious, at least not to me. And opposite of 30 is force of BX, so that'd be the sine. So I could say that the force of B in the X direction is force of B modified by the sine of 30. So I don't know if this makes sense to you, but rather than just calling them force of by and force of bx. Notice there's a bit of an advantage of rewriting them this way because notice there's only one unknown there. Force of b cosine of 30, force of b sine of 30. So I'm just getting the force of b and there's only one unknown there. Maybe that's an advantage. Okay. So again, I've got options. I could try the sum of the forces in x, the sum of the forces in y. I kind of got all kinds of options. But now that I know the force of A is 1 kilonewton, I'm feeling pretty confident I could get the sum of the forces in y. Since I have a lot of the answers to that, let's see if that actually works. Sum of the forces in y. Let's see, what do I got? We just figured out force of AY is 1 kilonewton. That's going up. And then we got the given 4 kilonewtons going down. And then we've got this force of AY going up. The force of BY, I'm sorry, force of BY going up. And we just sort of renamed that force of B times the cosine of 30. So notice that's only got one unknown in it, which is kind of cool. So I can calculate force of B, which is actually, again, kind of cool. It's that angled answer. It's the angled force of B that I'm getting. So that's kind of cool. So let's see if I subtracted 1 kilonewton to the other side, added 4 to the other side, I'd have -3 over there. And if I divided that by the cosine of 30, I got -3 point. Remember, that actually is force of B. And so notice I have the arrow apparently drawn backwards. That's kind of bothering me because it seems like isn't that what's happening? Isn't it pushing?
Wouldn't it be +3 in that equation? You add 4 to the other side?
Oh, you're right. That is, I screwed that up. So yeah, that's actually +3 on the other side. So my inclination was that it should be correct, and it was. Yeah, because I'm adding -4. I'm adding 4 to the other side. So yeah, it would be positive. So that means the arrow that I drew is correct. Thanks for catching that. Let's see. And so notice I've almost got all the reactions now. I got the force of AY. I know how strong that's got to be. I just figured out the force of B. It's 3.46 kilonewtons. And notice this is kind of interesting. Originally there was only one force in this going straight down. Isn't it kind of surprising, if you will? Like I was thinking for sure that this force of AX over here would be 0. Because there's no forces kind of working left and right. So shouldn't that be the case? But it's interesting because of the angle of this plate over here, because this plate is sitting here at an angle of 30 degrees. The fact that this thing is actually being pushed up on. The fact that this is being pushed on at an angle means it's also being pushed left. So that's actually kind of cool. So there is actually going to be a number for the force of A and X. And so let's see what that works out to be. What are all the sum of the forces in X? So the 4 does nothing. If I've drawn it correctly, the force of AX is actually going to the right. So that's positive. And we said the force of BX is actually pushing left. So that'd be negative. That's good. And we called it force of B times the sine of 30. So that's actually going left. And that's all the forces that are contributing left and right to this. And so notice we wouldn't be happy with this because it has 2 unknowns, except for the fact that we just got finished figuring out that the force of B was 3.46. And so I can actually solve this. So if I add 3.46 times the sine of 30 to the other side, I get 1.73. And all of my units were in kilonewtons. So, same as last problem. I've now figured out the reactions. I've figured out the breakdown. Notice force of A and Y is only doing 1 kilogram of work, whereas the force of B is doing more, as I was kind of suggesting. Since this 4 kilonewton force is closer to B, that means B is going to be doing more of the work on that side. So that doesn't surprise me that force of B is so much larger. And force of B is, you know, coming in at an angle. It's coming in at a 30-degree angle to the horizontal. So that's coming in at a weird angle. That's why 1 and 3.46 don't add up to 4. But if I converted this by doing exactly what we said over here, like multiplying it times the cosine of 30 and times the sine of 30, I could actually see if that was actually working. The force of B in the y direction must be 3 in the y direction, because 3 and 1 takes care of that 4 that we saw was being pushed down on up there. So you see, this is cool. Like it isn't new. It's still just equilibrium. It's just that you have to establish what's happening at these connections. What kind of forces can those connections resist? How's your brain? All right.
The angle is kind of hard to wrap my head around.
Yeah, that 30 is kind of strange the way it was drawn in there, right? Like it,
Yeah.
that's not obvious in this case. Well, I think the thing that makes the most sense is just to look at lots of examples. So let's look at another one. So stare at this one for a second. So notice this one appears to be cantilevered out from the wall. Here's the wall, and this is cantilevered out. And then there's kind of a strange pulley up here connected. So it's attached to the ceiling. So it's actually attached 2 different places. And then there's a weight over here that's kind of hanging down. And then remember, we got a cable. So that means the force here and the force here are going to be identical. And we're told that this is at a 2-to-1 angle, 2-to-1 ratio right there. So we're not given this as an angle like degrees. We're given it as a ratio. So, and then we're told, let's add that the beam weighs. I don't know if you noticed this from previous problems, but in the first problem that we did, does it make sense that you know, that wooden, it looks like a wooden beam anywhere, there's no weight associated with that? That's kind of fakey. Do you understand that? Like that does have weight, and that should be figured into this. So the book's problem, it didn't have this. I just added it myself. So I said, let's add that the beam weighs 42 pounds, because that thing appears to be drawn like it's out of steel. Like that's not nothing. So just because it's good practice, I am going to draw my own free body diagram this time. So I've got this beam. And because it is pin connected over there at A, then I know that I've got force of A in the Y direction that I can count on. And I've got force A in the X direction that I can count on, but it's pin connected, so there's nothing keeping it from rotating. So maybe now you can see why they attached it to the ceiling up here. Because if you had this weight hanging down and there was no attachment up there, this thing's rotating down, like it's not going to be in equilibrium. So they attached it to the ceiling. That kind of makes sense. So I've got those two forces that I don't know. Determine the tension in the cable and the horizontal and vertical components of reaction. At A, the pulley D is frictionless. That means we're not losing anything for friction around that pulley, which is not very realistic. And we're told the cylinder weighs 80 pounds. So I can go over there and add in 80 pounds. So finally a non-metric problem. And then I see this thing is attached here. Goes up to there. Comes back down. It's attached here again. And does it make sense because you at least assume that this is kind of a homogeneous piece of steel, like all the way across? Where would that 42 pounds act? I mean, it weighs 42 pounds, but remember, some of its weight is here, like there's 10 pounds, and there's 10 pounds, and there's 10 pounds. It's got weight everywhere across it. Does it make sense that really this is a continuous load all the way across this thing? There's actually arrows everywhere up there. But that's one of the reasons we worked with recently, how to reduce forces to not so many forces. Do you agree that although each one of those individual arrows might be like 5 pounds or something like that, spread all the way across the beam, it's a total of 42 pounds, and it would act exactly at the center of this thing? So it's 13 feet, so does it make sense it would act right there? So I don't have to think of it as hundreds of arrows. I can just think of it as one located at the center of mass of that shape. A little bit out of laziness, I have the dimensions up here, so I'm not going to re-add the dimensions to my drawing. I want to try to keep my drawing as clean as I can. I'll add to it as I go, but I have those two forces. I have the weight of the beam. I have the weight of that 80-pound cylinder pulling down. Let's see, I said if the beam's weight is in kilograms, we have to multiply by 9.81. But in this case, everything is in standard units, so that's already forces. So I don't have to worry about that here. They're not in kilograms. That's awesome. So what arrows am I missing? I mean, you always need to get all of your force arrows drawn in. Where am I missing force arrows? I've got 4 of them drawn in.
You're missing the force arrows of the pulley.
Yeah, the cable. And actually, if I'm thinking of the free body diagram as just the bar itself, does it make sense the bar doesn't know there's a pulley there? It just has a couple of arrows pulling on it. What should I call those? Like, I don't know what they are. Should I call them like force 1 and force 2?
It would be the same if they're pulled at the same angle, right? But so yeah, you have to differentiate between them because they're not the exact same forces.
That's exactly the question. What did we learn about the way cables work? I mean, if what's sitting at the top of this is a frictionless pulley, if this ends up with 100 pounds, what's the force that's going to be over here?
100.
It's also going to be 100. So those are exactly the same. So by me differentiating them force 1 and force 2, I'm actually acting like they're different, but they're not going to be different because that's a cable going around a pulley. So those are going to equalize. That's kind of the point. Now, however much forces each one has, they're going to end up the same. And so actually I'd be way better to label these like force 1 and force 1 because they're actually the same. Now they are being pulled at an angle. Force 1 is straight up. The other force 1 is pulled at a 2-to-1 angle. Maybe I'll do a little better and draw that in. But those two forces would actually be identical. If I do put that green theorem on 2 and 1, I get the square root of 5.
So aren't they acting different on the beam though? Because like we know there's a pole A, we know that, but you're saying the beam doesn't. The beam just has two forces, and aren't they different forces because of the angle?
No, they're not going to be the
Isn't it
same
just-
vertically. In other words, the force one at an angle, if this is 100 pulling straight up over here, then the beam is just going to feel that pulling straight up. This over here is also 100, but it's actually pulling at an angle. So that would break down into something in the X and something in the Y that's no longer 100, but it is still 100.
Oh, okay.
It's pulling at an angle. So the hard part of a free body diagram is you can't miss any of the arrows because you're going to be, adding all of these forces and setting them equal to 0. You're going to add all the moments and set them equal to 0. Notice the beam doesn't know what supports it's connected to. It just feels forces pulling on them. And again, I made assumptions about what direction those are going. I actually don't really know for sure if I have that right. You may remember that cables have to be in tension. So I know I have those two force ones correct, because that's the only thing a cable can do is kind of pull. And that sort of feels like it would be necessary for those to pull up, since 42 is pulling down and 80 is pulling down. It seems like force 1 and force 2 would, force 1 and force 1 would actually have to pull up to kind of counteract that. So again, I kind of have the same sort of conundrum I had before. So let's see, this was labeled C, in the sense that I don't really know where to start. Like, should I start with a moment calculation? Should I start with the sum of the forces in X, sum of the forces in Y? I don't feel super hopeful about the sum of the forces in X, because notice I have an unknown one here, either pushing or pulling. And then this one isn't doing anything horizontally, but this one is, and that's also unknown. So I basically have an unknown one pulling left and an unknown one pushing right. So does it make sense if I start with the sum of the forces in X, I'm gonna have an equation with two unknowns and I won't be able to solve it. It doesn't mean I can't write that down. But it means I'm not necessarily gonna make any progress. Do you see the same thing happening with Y? I've got this force in the Y direction that I don't know. And then I've got these two that are both making a difference in the Y direction. So it looks like my force in the Y direction equation would also have two unknowns in it. So this is just like last time. It's an advantage oftentimes to do the moment calculation first. And the cool thing about the moment calculation is you can choose what point you want it to rotate around to eliminate a whole bunch of the numbers. For instance, if I first started off here with the sum of the moments around A, do you understand the brilliance of starting? Why do I want to start at A?
Is it because you want to know the horizontal and vertical components of it?
Well, that's because these are unknown forces, right? I don't know what those are, but notice they're aiming right at A, which means they're no distance from A. So they're not going to provide any they're not going to provide any moment. Those aren't going to be a part of this calculation because they're aiming right at A. That's why I chose A, because then it eliminates those two. Now maybe I'll end up with an equation that doesn't have anything else. Now, can you appreciate starting at B would have been kind of a poor idea? That would have eliminated the 80, but I knew 80. So it's like, I don't really necessarily need that to be eliminated. I'd just as soon have that. And so then I will have a force of AY. Maybe I'll have a force of AX. Well, maybe not, because force of AX is pointing right at C. So I'm going to have force 1 and force of A, and I'm going to have two unknowns in it again. So I don't want to do this around B. So there's kind of a bit of an art to this. But I would like to, I don't know, caution you that it doesn't matter. Just because you wrote it out and you can't answer it right now, you will be able to answer it later. So it doesn't make any difference which order you write them in. Okay, so what are the sum of the moments in A? Well, where are all of these? Well, I've got this force one. And notice it's rotating in the counterclockwise direction, so that'd be positive. It's trying to rotate that way around A. And I know it's a distance of 5 feet. So force one times 5, so that's pounds times feet. So I've got that. That's cool. But then I have another force one. And it's also trying to get it to rotate counterclockwise. But again, do you understand? I don't want to leave that force one alone, because if I do, then the distance I need is perpendicular to that. So it's like I'd have to figure out what that yellow distance is. That's really hard. What I'd rather do instead is convert it, as we've been talking about, convert it to its XY components. In other words, take that force one. What part of it is vertical? What's the vertical modification if I want that to just be broken to its vertical version? Well, isn't its ratio 2 over the square root of 5? So if I multiply this by 2 over the square root of 5, now that's vertical only. I've taken that second force and now it's only vertical. And if that's true, that I've, recalculated that vertical, then perpendicular is 5 and 5. It's 10 feet away. Again, interrupt me if you're not seeing that. Now, what about the force? So that would be the force of 1 in the Y direction. Would you agree that force of 1 in the X direction actually goes this way and it's pointing right at A, so it has no distance, therefore it's not going to cause any rotation? Now, I will argue with that a little bit in the picture here. Do you agree that they kind of didn't do very good here? Where is that
Because it
actually
sits on
attached?
top of the beam.
Exactly. Isn't it attached right there? Is that aiming at A? Notice it's not aiming at A. It's a hair above it. Looks like an inch or two above it. But notice they didn't give me any distances. They didn't tell me what that was. So I think they're assuming I should ignore it. But they didn't do a very good job in the drawing. It would have been better if they kind of showed this cable attached, say, all the way down in the middle. Do you see what I'm saying? So that's a little deceptive. Do you agree with that? If they had given me a distance, then I would have thought they wanted me to include that. Now, as I said, it would be a tiny distance, right? I mean, it's going to be like 1 inch or something. So it's not going to make a huge contribution, but they're actually kind of wrong there a little bit. Let's see. So those two forces are causing rotation. The 42 is causing rotation. And because it's contradicting the other two are trying to get it to rotate counterclockwise. These two forces are trying to get it to rotate clockwise, which is negative. So that 42, and it's in the middle, right? It's right in the middle. Since this whole thing is 5, 5, and 3, 13, then that middle location would be half of 13 or 6.5. So it's 42 pounds. I'll include the units times 6.5 feet. And it's trying to get it to rotate negatively. And similarly, the 80 is going to do the same thing. 80 pounds, but it's at a distance of 13 feet. And so there's all the desires to rotate. Do you see why that was a wonderful equation to write first? Because it only has one unknown at F1. And so I'm able to solve it right now. So that's cool. So let's see if I add 80 times 13 to the other side and 42 times 6.5 to the other side. just to kind of be careful. What are you going to do with two force ones? Hopefully your algebra skills aren't going to let you down here. So hopefully you say, oh, I can factor force one out of both of those, leaving 5 plus, well, 10 times 2 over the square root of 5 would be 20 over the square root of 5. So if I take 13 divided by 13 divided by, and just draw that whole parenthesis out, 5 plus 20 divided by the square root of 5, I get 94.2. So I know what the cable must do. And again, obviously the practical side of that is you better have chosen a cable that doesn't snap when you put 94 pounds of force on it, right? So this isn't just academic. So that takes care of the cable. My 100 was a reasonably close guess. Notice they didn't ask us anything about this, I don't think. Determine the tension in the cable and the horizontal and vertical motion at pin A. They didn't ask us anything about what's happening up there at D. But if you appreciate that this cable is pulling 94 there and 94 there, that other 94 is at an angle, so that doesn't mean I just get to add them and call it 188. But that is trying to rip that out of the ceiling, right? So I could draw yet another free body diagram up there on the ceiling and figure out what's required up there. Since that looks like a fixed connection up there, then I could kind of assume it would have a force of y and a force of x. And I could actually figure out how much force is up there, and I would need to know that too. So they didn't ask me that, but your job as an engineer is to basically draw free body diagrams at every location. The beauty of which is you don't get confused because you're concentrating just on one thing at a time. I was first concentrating on trying to get this beam not to rotate like a helicopter, not to slide left and right, not to go up and down. And basically so far I've just succeeded in getting it not to rotate like a helicopter or like a propeller on an airplane. It's not rotating, it's not momenting around A, so that's cool. Okay, well now maybe I won't have as much trouble with kind of some of the other forces in the X and Y direction. So let's see what happens with that. I don't know, I wasn't thinking this time. I wonder what happens if I just do the sum of the forces in X. Again, I'm using the convention that right is positive, and so I've guessed, maybe incorrectly, that force of AX is going to the right. So that's cool. Force of AY is nothing in X, so I don't need that. 42 is not an X, 80 is not an X, those have nothing to do with it. This force one is going straight up, so it has nothing to do with it, but that other one does. So that other force one, and notice it's pulling to the left, so it'd be negative. And to be left, I would have to make its modification to horizontal. So the ratio would be 1 over the square root of 5. That's what the multiplier for that F1 would be. It's not a moment, so I'm not multiplying by anything. So do you see how if I had written this equation first, I would have just said, bummer, I can't solve it, but I'd be able to use it later. So if I wrote this first, and I just said, dang, it doesn't help me right now, I'll just save it for later. And then I went on and found out that force one was 94.2. Well, does it make sense? I can go down here and put in 94.2 now, and now it only has one unknown. So now I can kind of solve it later, so to speak. Cool. So all I have to do is take 94.2 times 1 over the square root of 5, add it to the other side. I am going to get a positive answer for force of AX. So that means I got lucky and the orientation that I gave it, aiming right, was actually correct. So that's interesting. I got around 42. I didn't round anything. And it wasn't exactly 42. It was actually 42.1 pounds. So they did ask me about the reaction at the wall over there today, so now I know that. I think that's just a coincidence that it happened to be so close to the 42 that was in this problem. And I would assume that if I jump to forces in the y direction, that'll have a similar kind of an answer, except for lots of those forces were in the y direction. I guessed force of AY was going up, so that makes it positive. I see 42 is going down. I see 80 is going down. I've got this force of 1 going straight up, and then I got the other force of 1, but to modify it, I've got to multiply it by 2 over the square root of 5. So I got 2 force 1s going up. One of them is not modified. The other one is modified by 2 over the square root of 5. And that's it. My free body diagram had all the arrows in it. Again, you can see now that had I written this first, that wouldn't have been very fun because it's got force of AY and force of 1. 2 unknowns, I wouldn't be able to solve it. But of course, now that I can say, hey, I know what this force is, it's 94.2. And I could basically add all of this stuff over to the other side and I'll have force of AY. So, so let's see, that'd be 122. I'd be subtracting 94.2 from that. And we'd be subtracting 94.2 times 2 divided by the square root of 5. I got force of AY to be negative 56.455, or negative 56.5 pounds. Now, so again, what that means is I drew the arrow the wrong direction. I'd like you to stop and make sense. Do you find yourself thinking, yeah, that actually makes sense, that's backwards? At first glance, when I was first doing this, I thought there's no way because look, we have 42 going down and 80 going down. Surely this is going to be pulling up. But a minute ago, we just discovered this was 94 pounds all by itself, and this was also 94 pounds. So these two are having to pull up so hard to keep this thing from rotating that they outpulled the 122 from this, and therefore this is actually backwards. It's actually going the other direction. Does it make sense? You would need to know that in terms of how it was attached to the wall. Maybe it makes a difference that that pull is up or down. Now, again, there's nothing wrong with just leaving your picture alone. Your arrow shows it going up. Your calculation says it's negative. You're done. But you could go re-change the arrow to aim the other direction and then change it to 56. That'd be fine too. Or you could even add this little note. So down then. In other words, you're just telling anybody that wants to know what that means. 56 pounds is 56 pounds. It's just a question of direction. The negative just means down. So
Doug, is that kind of like a weird result? Because like if you have a pulley with cables, like you're never like, it's usually just to balance everything out, right? You're never like, oh man, these cables are pulling too hard.
Yeah,
We should reinforce. Yeah, we should reinforce the bottom hole so that we don't, like, you know what I mean? It seems just like a weird answer.
yeah. So the issue with the pulleys is it was entirely the moment that determined what those had to be up to. Because this thing really, because of the 42 and the 80, wanted badly to rotate clockwise. And so the cables had to do apparently 94 pounds a piece in order to contradict that. And notice that number is as large as it is because it doesn't have the distance. That cable's a lot closer to A. It's attached a lot closer to A than that 80 pounds is. That 80 pounds is 13 feet away. So the 80 caused a ton of rotation, since rotation is force and distance, and that's a really big distance. So basically, I had to pull back quite a bit harder as a result. So basically, this is just somebody saying, well, why don't we just attach this thing to the ceiling with a cable so that it'll equalize? And maybe you can appreciate it's not like they had to do it that way. Does it make sense? They could have just attached this cable directly to the ceiling and not had that one at all. Maybe that you can probably appreciate, since we doubled the cable, that weight would have been a lot bigger. It would have been like 180 pounds or something like that. But for whatever reason, they just said, let's attach it this way. And that's kind of cool that the cable will equalize as a result of that. But that is a weird arrangement. That's kind of a lot of trouble to go to have a pulley on the ceiling and all of that in order to bring this thing about. So the main takeaway here is you're really stuck with, at least in 2 dimensions, and most problems are 2 dimensions. You're kind of stuck with some of the forces in X, some of the forces in Y, some of the moments. And then just do whichever one you can answer. If you're algebraically structured this way, don't try to solve any of them. Write all of them out. Just write all 3 of them out. Do the sum of the forces in X first, some of the forces in Y next, some of the moments last. And then once you get them all written out, then say, okay, which ones can I solve? In this case, I never had to solve 2 equations, 2 unknowns, because the sum of the moments equation only had 1 unknown. So then I was kind of on my way. Interesting side note. Given that I think we should save the next problem I have for Thursday, because we're kind of running out of time. I did the sum of the moments around A, and I explained to you why I thought that made the most sense. But just for the fun of it, I wonder what would happen now if we kind of went back just to, I don't know if the right word is check. But would you agree that we successfully made this thing not rotate around A? And so it's not rotating around A, but does that mean it's also not rotating around C? Or maybe some of these other points? They got this one labeled at B. They never labeled this point over here, but what is it rotating around B? Is it rotating around C? Let's just see what happens now that we're sort of done calculating. Let's see what the sum of the moments around C would be, just for the fun of it. Let me go back in and let's try and get rid of all the junk that we don't need to look at. Ooh, that was too much. We'll call that good. So let's see what's happening around C. Well, the force of AX is aiming right at C, so it doesn't do anything. But the force of AY definitely wants it to rotate this way. Oops. Definitely wants it to rotate that way, which we call negative. So the force of AY multiplied by a distance of 13. And I'm seeing that would be clockwise rotation, so I'm calling that negative. And then I have, let's see, 42. Trying to get it to rotate the other way. That's actually positive. And that was a distance of 8, if I remember right. So this is the disadvantage of not including those measurements. So 5 feet there and 3 feet there. So that's a distance of 8. And then 80, of course, is no distance at all. So 80 is not going to do anything. But we have the force of 1. Actually, what's wrong with 42? I did that wrong. You guys should have interrupted me. Where was 42 located?
In the center. So 6.5.
It's in the center, so it's 6.5.
Isn't it going clockwise? So it shouldn't be negative.
No, because it's
Oh, 'cause
pulling
we're-
in this direction, and so it's wanting to go that way, which is counterclockwise.
Right.
And then we got this force 1, which is again trying to get it to rotate clockwise. So that's negative. It's going straight up. That's what's the distance of 8. That's why I caught it, because I was about ready to do that one. And then lastly, we also have the other force 1, but we got to make it vertical by multiplying it by 2 over the square root of 5. And then it's a distance of, I think, only 3. Yeah, it's only a distance of 3. So there's its vertical component. It's a distance of 3 away. Smooth. And it would also be negative because it's trying to do clockwise rotation. Is that it? Do I have every? So the question is, what's kind of weird about this is notice we actually have the answers to all of these. Don't we know that force of AY was negative 56.5? And don't we know that force 1 was 94.2? So we actually have no unknowns. That's rather terrifying. I wonder what this is going to be equal to then. You punch it in, what do you get? Negative 56.5 times 13. Notice that's a negative times a negative. So you have negative 56.5. So that's actually turned into a positive. I missed that. And then plus 42 times 6.5 minus 94.2 times 8. And then minus 94.2 modified by 2 divided by the square root of 5 multiplied by 3. I'd like you to take the time to plug that in before we're done. What do you get?
I got the moment around C is negative 1467. Okay, I was like, that seems. I was nervous. I was wrong.
I got something wrong with it.
I got the same thing.
So you did all notice this is negative and this is also negative.
I didn't do that, so that would make that positive.
Yeah, it's actually fixing it to a positive. So you really should have 56.5 times 13. If everything goes well, at least if I didn't screw it up, I got 1.13.
Yeah, that's what I got.
Notice it's not equal to 0.
Okay.
But I'm guessing this is just rounding because those two measurements that we had, we rounded, right? It wasn't really 94.2, it was 94.16, whatever, some change. And then I can't remember about 56.5. Was that rounded? I used the rounded 94.2 answer to calculate that. And so the point is it's close to 0. And frankly, it actually had to be. That's the reason I called this checking my work, because if it's not rotating around O or A, then it must not be rotating anywhere. So I could actually redo this around any point along that I wanted, and I should get the sum of the moments is nothing. It's not rotating. I've stopped its rotation in every respect. So that's kind of cool. If you want to let's see. .1605. Force of 1 was actually 94.1605. That's accurate to 4 decimal places. And then if I use that number back here to recalculate force of AY, then it's probably not going to be 56.5. It'll be slightly different. My guess is if I redid this, I'll get something a lot closer to 0. Maybe I'll get 0.2 equals 0 or something like that. But this should say 0, except for rounding it is. So my hope today is that you don't see this as terribly hard. You do have to draw a really effective free body diagram and not miss any of the arrows. And obviously the backbone of that is establishing, what kind of a connection do I have so that I get the right number of arrows in the right locations here. This is pin connected. So I know that that's a horizontal and vertical component, but not a rotational component. And I think it's not obvious, but cool that I redrew. I think this was a good time to redraw the free body diagram because, as I said, the beam doesn't know there's a pulley up there. It just knows that it has a couple of forces pulling on it. That's all it feels, if you will. It doesn't know they're the same. You do, because it's actually a pulley. And that would have made this a lot worse, actually, if that was just 2 different wires that were hooked to the ceiling in random locations, in which case they weren't equalized. That would have made this problem harder. So Thursday, we'll take a look at this beauty. This has kind of a practical sort of a feel to it in the sense that it looks like, some kind of a wrecking ball. And then you can see that, there's an implication that that ball weighs a lot. And again, it's interesting to note when you look at CB that it looks like a rope, look like a cable. Can you appreciate that CB would be in tension? It would be getting stretched longer as a result of that weight pulling down on it. Whereas AB looks like it's a bar. So it's not in tension, it's in compression. So could we figure out how much force is in the cable and in that strut? Your book often calls AB a strut. Do we need to note that both of those attachments down there are pin supported? They can rotate. Do I need to include that? I sent that to you earlier. More than welcome to kind of play with it, but you should be able to tackle a decent chunk of the chapter 5 homework. What I want to do on Thursday is do this problem and then do something kind of cool and practical, almost like a project where I'm going to hang kind of a a stick from the wall and I'm just gonna lean it against the wall over there. And then I'm gonna hang a weight off of it over here. And you can appreciate if that's not actually attached to anything over there at the wall, that's not gonna work good. But then I'm gonna come back and add a cable back to the wall up here so that now that can't move. Again, this is kind of a classic engineering application because I'm making a support for a crane or I'm making a sign that overhangs a sidewalk or something like that. So the fact that there's a cable up there, if we do this in class on Thursday, which I hope we will, we can actually put a spring scale right there and actually measure the amount of force that's up there and see if our calculation justifies that. See if we actually can figure out how much force is at that location. And then given that this is just pushing against that wall over there, this isn't attached in any way. I wonder what difference that'll make. And so we'll have a weight here, but then we'll also have the weight of the stick itself. How much does the stick weigh? But I want that to be realistic in the sense that we're going to weigh it. I'm not just going to tell you what it is. I'm going to say, put it on a scale and here's its weight. All right. Let's call it a day.
Thanks, Doug.
Thank you all. Appreciate you showing up on Zoom. Sorry, I was coughing in your ear the whole time.
Oh, it's fine. Hope you feel better.
Thank you.
Thanks, Doug. Feel better.
Thank you.
Thanks.